Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Cyber Physical Systems ISC. Today's talk is by Professor Ashish Hota, and he will be speaking on interplay of strategic decision making and spread of epidemics on networks. Professor Hota received his BTech and MTech degrees from the Indian Institute of Technology, Kharagpur in 2012 and PhD from Purdue University, USA in 2017, all in electrical engineering. He was a postdoctoral researcher with the Automatic Control Laboratory, ET at Zurich in 2018. He is currently an assistant professor with the Department of Electrical Engineering, IIT Kharagpur. He received the Outstanding Graduate Researcher Award from the College of Engineering, Purdue University in 2017 and the Institute Silver Medal from IIT Kharagpur in 2012. His research interests are in the areas of game theory and behavioral decision theory, stochastic optimization, control and learning, and resilience and security of network systems. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Professor Hota directly or type them in the chat box and we'll moderate it with him. Over to you, Professor.
Thank you very much. First of all, very good afternoon to all of you. And I thank the organizers for inviting me to speak at this excellent seminar series. So today I will talk about some of our recent work on the interplay of strategic decision-making and spread of epidemics on networks. So as we have seen for the past 2 years with COVID, infectious diseases spread through society by exploiting interaction among individuals. Individuals choose their level of interaction in a selfish manner and often subject to bounded rationality by evaluating the trade-off between benefit of interacting with others and the potential risk of becoming infected. In this talk, we will model this decision-making process using game theory and consider the implications of game-theoretic decision-making on the evolution of a broad class of epidemics called the susceptible-infected-susceptible epidemic. So there has been a large body of work on mathematical models of epidemic evolution. There is also a considerable body of work that applies centralized and game theoretic approaches for containing epidemics. However, most of this work assumes that epidemics evolve on a network that is static. However, in practice, the network evolves in response to the epidemic and in a time scale that is comparable to that of epidemic evolution. So in part one of this talk, we examine this aspect in the context of activity-driven networks, which is recently gaining popularity. Then we examine the problem in a slightly different context. In particular, existing game theoretic models of epidemics often focus on structural properties of equilibria, and they assume that the individuals play their equilibrium strategies and analyze epidemic evolution under these strategies. However, a large population of agents do not suddenly start playing equilibrium strategies. There is often a learning process, for example, best response dynamics or evolutionary learning process such as replicator dynamics, through which they discover their equilibrium strategies. Now, what happens when these learning dynamics evolves in the same time scale as that of epidemic evolution? So that is the part we focus on in part two. We'll try to spend more time in part one, and then in part two, we will only cover the main results. So let us move on. So the first part is a joint work with two of my students, Tanya and Kavish, who have now graduated. The setting formally is as follows. Let capital V denote a set of n individuals or nodes with ith individual denoted by Vi. These nodes can belong in one of two possible epidemic states, susceptible or infected. If at time k, node Vi is susceptible, we say VIK belongs to S. If it is infected, we say VIK belongs to X. These epidemic states evolve as follows. If node Bi is susceptible at time k, then it becomes infected at time k plus 1 if it catches the infection from one of its infected neighbors. The probability of becoming infected from one neighbor is the infection rate denoted by beta, and the infection caused by different neighbors are independent of each other. If a node is infected at time k, then it becomes susceptible at time k plus 1 with probability delta. Otherwise, the state remains unchanged. Now, this process can take place over a static network, but as promised, we will consider the epidemic state evolution on a dynamical network defined as follows. Now, at time k equal to 0, we assume that each node is initialized to be either susceptible or infected, and the network is empty. That means there are no edges between these nodes. At any time k, each node Bi activates with a certain probability. If the node is susceptible, its activation probability is pi Sik, and if it is infected, its activation probability is pi Xik. After it activates, it chooses Di nodes uniformly at random and forms edges with them. So Di is essentially the degree of this node. Now, once the connections are formed, epidemic states get updated according to the previous definition. Now, these edges are discarded at time k plus 1, and we again start from an empty network, and the process repeats itself. The point to note here is that the network is time varying and it evolves probabilistically. And so far, these activation probabilities are node specific, time varying, and state dependent. In this context, we derive individual and degree-based mean field approximations of exact state evolution. We formulate a game-theoretic model where nodes choose activation probabilities subject to bounded rationality, followed by analyzing epidemic evolution under the equilibrium activation probabilities. Okay, so first consider the exact state evolution. In order to describe the state of each node, we introduce an indicator random variable, capital Xi, which takes value 1 if the node is infected at time k, and value 0 if node Bi is susceptible at time k. Then the exact state evolves in discrete time according to the equation stated here. Now, it means the following. If at time k, this node is infected, then this entire second term becomes 0. And the first term is either 0 or 1, depending on the value taken by n delta. So n delta is the notation for any Bernoulli random variable, which takes value 1 with probability given in the subscript here. So with probability delta, n delta takes value 1 and Xik plus 1 becomes 0. So this represents the transition from infected to susceptible. Similarly, the second term represents the transition from susceptible to infected. So a susceptible node becomes infected with probability 1 minus the probability that none of the infection events become successful. So that means this is the product of the non-successful infection events from each of the other nodes present in the network. So for an infection attempt to be successful, we need 3 conditions. One is that the 2 nodes must be neighbors, which is captured by the indicator random variable aijk. The other node must be an infected node, and the infection must be successful with probability beta. So these 3 events are captured by this product term here. Now, the exact state evolution in a society with n nodes actually has 2 to the power n possible states, which is prohibitive to analyze. Therefore, in the epidemic literature, we often resort to mean field approximations of the exact state. Therefore, we keep track of the quantity little xik, which is expectation of big xik, or the probability that node Bi is infected at time k. Now, according to this proposition, little xik evolves according in discrete time in this manner. Here, beta ij is the effective infection rate from node j to node I. And this is a product of two quantities. One is beta, which is the infection rate of the disease itself. And the second term is essentially the probability of node VI in susceptible state forming a connection with node VJ in infected state. Now, this connection is essentially the union of two events. One is VI activating itself and choosing VJ as one of its neighbors. This happens with probability pi SIK, that is the activation probability of this node at time k, times the probability that VJ is one of the nodes chosen by VI. And this is nothing but DI divided by n minus 1, where n is the total number of nodes. Similarly, the other event is that of VJ, an infected node activating itself and forming a connection with VI. And this happens with probability pi xjk times d bar j. Now, the union of both these events is essentially the term inside this square bracket. The derivation is not particularly difficult. We start by evaluating the expectation on both sides of the exact state evolution. To deal with the product term, we apply Weierstrass's product inequality, which gives us this upper bound. And in the final step, we assume that the infection states of node VI and node VJ are independent. This is a reasonable assumption in this context if the number of nodes is large, and particularly because we do not have a fixed network structure. So the network is being created fresh at every time step, and therefore two specific nodes are often not in contact with each other. Once in a while, they become in contact. So there is no reason that the infection states would be strongly coupled or strongly correlated. So under that assumption, we obtain this mean field approximation. While the previous mean field approximation helps us track the infection probability of each individual node, in a large network, it is often prohibitive to keep track of these infection probabilities. So therefore, we would mostly work on a more coarse version of mean field approximations called the degree-based mean field approximation. And later on, when I introduce the game theoretic setting, we will largely be working in the degree-based framework. So formally, let this population of n nodes have degrees from this set capital D. That means nodes can have degrees such as D1, D2 up to certain D max. Let ND be the proportion of nodes with degree D. And let XDK represent the proportion of degree D nodes that are infected at time K. Now this XDK would be the primary quantity which we would be keeping track of. Finally, we assume that all nodes of a particular degree and a particular epidemic state have an identical activation probability denoted by pi dsk or pi dxk, depending on whether they are susceptible or infected. Under this framework, we define the degree-based mean field approximation similar to the individual-based mean field approximation, where the only difference is that instead of beta ij, we have beta dt, which captures the effective rate at which an infected node of degree T transmits the infection to a susceptible node of degree D. Now, this right-hand side is obtained from the individual-based mean field approximation formula by noting that in the previous formula, the terms inside this summation, all nodes Bj with the same degree would contribute the same amount to beta ij. So with that observation, we came up with this definition here. Now, so far, we have assumed that these activation probabilities are exogenous. However, we would mostly focus on a game theoretic setting where these activation decisions are taken by the nodes in a decentralized manner. Okay, so any questions so far before I introduce the game theoretic model?
This is Rajesh here. Can I ask a question?
Yes, please.
One clarification that I would like to have is the graph changing with time? You had an Aij of k.
Yes.
And if that is the case, when you have the degree that is essentially set to be a constant, does the node's degree persist across one graph from one time point to another?
Okay, so let me clarify here. Thanks for the question. So edges are formed in two ways. Either the node activates and forms connections, or somebody else activates and chooses this particular node as the connection. Now, if a node activates, it chooses exactly di other nodes to form connections with. Okay. However, any number of other nodes can activate and choose it as one of their neighbors. And that process, this node does not have any control over. Okay, so if I go out, I talk to di other people. But if I stay home and a lot of other people come to meet me, I cannot really prevent them from meeting. So it would be rude to throw them out of my house.
So x d of k then would be for a d out degree nodes, fraction of nodes with d out degree who are infected.
Yes. However, once the degrees are formed, they lose their directionality. So both types of edges are equally capable of transmitting infection.
Okay.
So once the edges are formed, you don't care how they were formed.
Yeah. Thank you.
Yeah. Any other question?
Maybe one more question related to the model. The contact rates, etc., seem to depend on the degree D. Was there some physical situation that motivated this particular problem, or is it something that you had in mind as a challenging question for which you wanted an answer?
Yes, so a lot of the work on activity-driven networks usually operated in the homogeneous setting, where if a node activates, it forms one other connection. It's like a completely uniform and homogeneous setting. So we wanted to see what happens when we relax this assumption. So that was the primary motivation. And also this should lead to a more richer set of dynamics. And in the population also, we have many individuals whose job requires them to interact with a lot of other people. And there is also a large section of society who is like grandparents or homemakers who do not interact with many people. So in that way, our society is quite heterogeneous. And therefore, this framework with heterogeneous node degrees would better capture compared to the simpler assumption of homogeneous node degrees.
So my question was something different, that the heterogeneity and the contact rates depend on the D. So heterogeneity, I kind of agree that that is something which is natural.
Yes.
But the contact rates depend on the D. The B, is that correct? The pi x, I mean, the notation is a little unclear, but
no.
There's a D-dependent rate. Yes.
So well, for this result to be true, these contact rates are, these activation probabilities are completely individual specific.
I see.
Now for the degree-based mean field approximation, we assume that all nodes of a particular degree choose an identical activation probability. That is because when we consider the activation game, where we ask the nodes are choosing their activation probabilities themselves. So at the beginning of any time period, so the network is completely empty. So therefore, all degree D nodes who are susceptible face an identical decision problem. So if they activate, they would form a certain number of connections with the overall population. And then their infection rate risk would be similar, exactly the same before forming of the network. So therefore, at the beginning of time k, they all face the same decision problem. So to keep things tractable, we assume that they adopt the same strategy, which leads to all nodes of degree having the same activation probability. Okay. And since we have already derived the mean field approximation under that assumption, we would then be able to plug in the equilibrium activation probabilities in place of these guys.
Okay, thank you. Yeah, please go ahead.
Yeah. Thank you. So now let us formally introduce the decision-making process here. At each time k, each node myopically decides whether to activate or not. If a node activates, it receives benefit of 1, but that naturally comes with a higher risk of becoming infected, because when you activate, you have to form a certain number of connections with other nodes. And if you become infected, there is a perceived loss of amount L. Now, as I was describing just now, all nodes of a given degree and disease status face an identical decision problem. Hence, we assume that they adopt the same strategy, meaning they choose the same activation probability. The strategy of a node is essentially its activation probability, denoted by pi dzk. And the strategy profile of all the nodes is the concatenation of these activation probabilities across all degrees and across infection states. Now, let us define the utilities of the players. For a susceptible node with degree D, if it activates, it receives the benefit of 1, but experiences a cost, which is the product of the loss of an infection L times a risk factor RD, which depends on the strategy profile, that is the activation probability chosen by everybody else, the current level of infection prevalence that is known to the players. So X bar K is essentially the information available to the nodes about the disease prevalence at time K. I'll specify exactly what I mean by that in a second. And this is conditioned upon the fact that the node activates. When a node does not activate, there is no benefit, but there is still a potential risk of becoming infected, because even though this node does not activate, somebody else might activate and form a connection with it. And that risk factor is denoted by RD, which is a function of pi X bar K, and conditioned on the fact that this node does not activate. Now, the utility of an infected node with degree D is much simpler to define, because when the node is infected, it is already infected. There is no further risk of infection. It's already sick. If it does not activate, it does not receive any benefit. Nothing happens. Utility is defined as 0. If it activates, it receives the benefit of 1, but experiences a cost, which could represent the penalty of violating quarantine norms when you are infected, or it could simply represent the fact that if you are infected and you go out, interact with others, you may fall sick. Your condition may worsen. So that is captured by the parameter C here. Now, having introduced these utilities, we now talk about how nodes choose their activation probabilities. Now, if I am a susceptible node with degree D, I can simply calculate the utility upon activation, the utility when I do not activate, and pick the action that gives me higher utility. That would mean that the strategies are essentially pure strategies. In this work, we consider a slightly more general choice model, which is the logic choice model, where a degree D node activates with probability denoted by pi star lambda dz, which is a function of the current infection prevalence known to the player and the strategy profile of the others, and defined as the ratio of e power lambda times utility upon activation divided by e power lambda times utility upon activation plus the e power lambda times the utility when it does not activate. And essentially, it boils down to the difference between the utilities when it activates and when it does not activate. So this pi star lambda dz can be viewed as the best response of a node with degree D and infection state Z to the strategy profile pi. Having defined the best response in this way, we did not specify what we mean by the term lambda. So lambda essentially is a parameter that controls the degree of bounded rationality. When lambda equal to 0, then this activation probability is 0.5. That means node activate or not activate uniformly at random without looking at what others are doing and what is the current level of epidemic prevalence. When lambda goes to infinity, activation probability approaches 1 if the utility from activation is bigger than the utility when you do not activate. That is, this delta U term is strictly positive. So that means as lambda goes to infinity, we approach a pure strategy. For intermediate values of lambda, an individual chooses an action that gives it higher utility with a higher probability. So more often you go for the action that gives you higher utility, but once in a while you also make a mistake and choose the action that gives you a smaller utility.
Professor, we have a question in the chat.
Yes.
The assumption that each activated node creates an edge with a random node chosen uniformly suggests that this is mainly applicable for small, close-knit communities. So how well does the mean field model approximate the original model?
Okay, it's a fairly good question. So we don't have any quantified results on the error between the mean field model and the original model. But from the derivation, the mean field model would be fairly accurate when the number of nodes is large. So this could, if I try to relate it to practical scenarios, this model could be relevant in crowded urban environments like slums or similar crowded areas when there is a large number of people. And when they decide to go out, they would bump into a lot of other people at random. And yeah, so that could be a situation which is fairly well captured by this model, is what I would say at this point. So does that answer your question?
Yeah, that partly answers the question, but just taking your example further,
yes,
if we take the example of slums and such things, then there is also a spatial structure, right? I mean, this geographical neighbors of a person, right? So the neighbors, immediate neighbors of a household, they're probably more likely to run into those people, right? So
right,
yeah.
No, that is true. That is true. I completely agree. So one can sort of think of extending this framework to capture an already sort of inbuilt geographical substrate where you are more likely to meet certain nodes over others. But that is certainly a very useful point.
Okay.
Another possibility like hostels, for example, in universities, hostels have a lot of students. That could be one situation. Yeah.
Right. Yeah. Okay. Yeah. Thanks.
Thank you. Now, having introduced the logic choice model, we now formally state the notion of equilibrium that we consider here. So we consider the notion of quantal response equilibrium defined as follows. So a strategy profile pi lambda ne is a quantal response equilibrium if for every degree and every epidemic state, the best response of a node of degree d and epidemic state z to the strategy profile pi lambda ne defined through the logic choice model is nothing but the activation probability specified by the strategy profile for nodes of the same degree and epidemic state. So this is very similar to the definition of Nash equilibrium that we are mostly familiar with. So essentially, this best response defined by the logic choice model defines a mapping from the strategy profile to itself. And the strategy profile, that is the quantal response equilibrium, is the fixed point of this mapping. In other words, at the QRE strategy profile, the probability with which a node activates under the logic choice model coincides with the probability specified by the strategy profile. Now, in this setting, there is a finite number of subpopulations, since we already assumed that the degrees are bounded by Dmax, and all nodes of a given subpopulation choose among two possible strategies. So therefore, there always exists a quantal response equilibrium of this type. Now, I have defined the best response and the equilibrium for a generic delta U dz. Now, as promised, I will specify what we define the risk factor and X bar K for this work. Now, so recall that X bar K was the information available to the nodes at time K about the disease prevalence. And this we define to be the proportion of infected nodes across all degrees. So instead of assuming that nodes are aware of the proportion of infected nodes for each individual degree, we reduce the cognitive burden on them. And in fact, from testing data, etc., we know the aggregate level of infection and not the infection prevalence among different subgroups of individuals. So therefore, we assume that X bar K is the proportion of infected nodes across all degrees. Now, the risk factor RD, we define to be the probability of a susceptible node of degree D becoming infected at the immediate next time step if it activates, given the current strategy profile of all the nodes is pi, and the infection prevalence is X bar K. Now, we have this lemma which says that when the maximum degree is much smaller than the total number of nodes, then this difference in utilities can essentially be approximated by this simple quantity 1 minus L beta D X bar K. So this is a fairly sort of nice finding. So we actually do calculate rigorously these risk factors. And this, when D max is much smaller than N, this leads to a large degree of simplifications, and finally we are left with this term. So what this essentially says that the quantity 1 by L beta D essentially acts as a threshold, and when the total or the average infection prevalence X bar K is smaller than this threshold, then delta UDS is positive, otherwise it is negative. Okay. Now, with this observation, we can now state the activation probability of a degree D node at the quantal response equilibrium. Now, for a susceptible node, it is given by e power lambda minus lambda L beta D X bar K divided by the numerator plus 1. And for an infected node, it is e power lambda 1 minus C divided by numerator plus 1 as before. So recall that when X bar K is less than this threshold 1 by L beta D, then activation is the preferred option and vice versa. Now, at a given infection prevalence, nodes with a larger degree will have a smaller threshold, and therefore they are less likely to activate. And which also makes sense because larger degree nodes, if they activate, they are more likely to become infected as they form a lot of new connections. Now, these activation probabilities also suggest that nodes use the current state information X bar K as feedback to choose their activation strategy. Now, for infected nodes, the utilities were constants and they did not depend on the strategies or infection prevalence, and therefore the activation probability under equilibrium is also a constant depending on the factor C. So what we do next is that we consider the evolution of the epidemic states, that is the proportion of infected nodes for each degree under these QRE activation probabilities. So we basically, in place of the exogenous constants in the DBMF approximation, we now use the activation probabilities at the quantal response equilibrium. Now, the resulting dynamics is highly nonlinear, and it is challenging to obtain theoretical results about the equilibrium and convergence behavior. Therefore, we consider the special case and we try to derive certain theoretical results on that. So we mainly focus on the regime where the rationality parameter lambda is very large, approaching infinity. And for infected nodes, the activation, the cost or the penalty upon activation exceeds the benefit. In this regime, the activation probabilities for infected nodes approaches 0, and the activation probabilities for susceptible nodes takes one of these three possible values. So when X bar K is less than the threshold, activation probability approaches 1. When X bar K is bigger than the threshold, the activation probability approaches 0. And at the threshold, nodes are indifferent between activating or not activating, and then the activation probability is 0.5. With a slight abuse of notation, we now write the closed loop dynamics in this form here. So when X bar K is strictly bigger than 1 by L beta D, then susceptible nodes do not activate, infected nodes also do not activate. Therefore, there is no way these nodes can get infected anymore. So the XDK plus 1 is, in fairly simple terms, 1 minus delta times XD, and it reduces at rate delta. When x bar k is smaller than the threshold, then susceptible nodes activate with probability 1. And in that case, we have the second term here, which is the term that possibly increases xd by leading to new infections. Now, before we analyze this closed loop dynamics in full generality, we first consider the case when all nodes have the same degree d, that is, nodes are homogeneous with respect to their degrees. Then we have the following proposition. So let beta and delta be between 0 and 1 naturally, because they are probabilities. Additionally, let beta d be less than 1. Now, this is an assumption which is required to make sure that this discrete time dynamics remain bounded between 0 and 1. For the continuous time counterpart of this dynamics, if one would study, then this assumption would not be required. Now, we have three possible outcomes in the homogeneous case. Now, when delta is bigger than beta d, then xd equal to 0 is the unique equilibrium of the dynamics. And this equilibrium is asymptotically stable. And for any initial condition, xd decreases and converges to origin, or that is the disease-free state. In the second case, and here the disease is decreasing solely because the curing rate is sufficiently high, or the recovery rate is sufficiently high. When that is not the case and delta is less than beta d, then there are two possible equilibrium points, 0 and x star d, where x star d is defined by 1 minus delta by beta d. Now, this x star d would be an equilibrium of this closed loop dynamics if it is less than or equal to 1 by L beta t. So why that happens can be viewed from this second figure on the right column here. Now, if the infection starts with xd0 larger than 1 by L beta t, then we know that the infection will reduce at rate delta. And finally, it will cross over to the site where xd is less than 1 by L beta t. Now, in this region, the effective dynamics is essentially the second dynamics. Now, the second dynamics has two equilibrium points. One is 0 and one is x star d. And in this case, x star d is also less than or equal to 1 by L beta d. That means both the equilibria are in the correct region. And because x star d would be the stable equilibrium when delta is less than beta d, the dynamic xdk would finally converge here. So if initial infection level is smaller than x star d, it would increase and converge at x star d. If initial infection level is larger than x star d, it would decrease and converge to x star d. So finally, we have the third case, which is when delta is less than beta d and x star d is bigger than 1 by L beta t. That means x star d lies somewhere in this region. Now, in this case, if the initial infection is less than the threshold, then level of infection will increase. When it exceeds the threshold, then the infection will reduce because beyond the threshold, nodes stop activating and infection reduces at rate delta. Therefore, the infection will finally settle down around this threshold point 1 by L beta t. That is, this threshold would essentially act like a sliding surface for this switch dynamics. And the disease will not converge to x star d anymore because x star d is at a region where the only dynamics that plays a role is 1 minus delta xdk. Okay, any questions at this point? Okay, moving on. We have a simple numerical example here to illustrate the above phenomena. So in the left-hand side figure, we choose the parameter L to be equal to 2. Here, x star d is 0.5 and 1 by L beta d is about somewhat around 0.6. X star d is smaller than 1 by L beta d. So as our theorem suggests, the DBMF approximation converges to x star d. Now, the actual epidemics, where we simulate n nodes, we have started actually with 100 nodes, and we simulate the exact activity-driven network formation process and the exact state update. And the simulated version is slightly below the DBMF approximation, but it still remains somewhat close to X star D. When we increase the value of L, the threshold reduces and falls below X star D. In that case, both the simulated infection state and the DBMF approximation converges to 1 by L beta D. And the same thing continues to happen as we increase the value of L more and more. So therefore, the parameter essentially L beta D, that is the degree of the nodes, the loss due to infection, and the native infection rate of the disease, they together where the epidemic will finally converge in this game theoretic setting. Now we try to reason about the closed loop dynamics when node degrees are heterogeneous. Before we talk about the main result, we first establish an intermediate result. Now consider the discrete time dynamics shown in blue here. So this is essentially the dynamics when all nodes that are do not activate and times the average is less than beta times the average degree, then there are two possible equilibria. One is a disease-free equilibrium, and the other is an endemic equilibrium, where the proportion of infected nodes for every degree is strictly positive. And then there is also an additional condition under which the endemic equilibrium is asymptotically stable. So for any initial condition that is not at the origin, the dynamics will converge to the endemic equilibrium. Now, having this result, we now denote, we introduce two notations. One is X bar star D prime, which is the proportion of infected nodes across all degrees at the endemic equilibrium of these dynamics, followed by X bar star star D prime, which takes value 0 when disease-free equilibrium is the unique stable equilibrium, and value X bar star D prime when the endemic equilibrium exists. Now, with this notation in hand, we now finally introduce our main result. Now consider the closed loop dynamics, which we obtain when nodes choose their activation probabilities under the quantal response equilibrium strategies, and the rationality parameter goes to infinity. Then we have two possible, there are 2 points to make. When delta is bigger than beta times the average degree, that means the recovery rate is sufficiently high, then the disease-free equilibrium is the unique equilibrium, and it is also asymptotically stable for the entire region. Now, when it is not the case, then there is a possibility that a non-zero endemic equilibrium will exist. Now, it would exist if and only if two conditions are satisfied. The conditions are stated in terms of this quantity dr, which is defined to be the largest degree for which X bar star star for nodes D1 up to D bar is less than or equal to 1 by L beta dr. To explain this, please note that 1 by L beta dr is essentially the threshold beyond which susceptible nodes stop to activate. Now, when D1 is, since D1, if we assume that D1 less than D2 less than D max and so on, then 1 by L beta D1 will be bigger than 1 by L beta D2 and so on. So that is 1 by L beta dr is essentially a decreasing function of dr. Similarly, we can also show that X bar star star for degrees D1 up to dr is an increasing function of dr. So as I add more and more degrees to this possible set, the infection prevalence at the endemic equilibrium would increase. So therefore, there would be a certain point, there would be a certain maximum degree dr at which this condition would be satisfied. Now, there are two cases. One is that this condition is satisfied at Dmax all the way up to Dmax. That means 1 by L beta D max, even when it is smallest, is larger than the infection prevalence at the endemic equilibrium. In that case, there would be a non-zero endemic equilibrium that would exist. The second possibility is that when dr is less than d max, and this x bar star star from with degrees d1 to dr, it has to be less than 1 by L beta dr, but it is bigger than 1 by L beta dr plus 1. So in this case also, there would be a non-zero endemic equilibrium that would exist. And we also have the precise values that would represent the infection prevalence at this equilibrium. So for all degrees bigger than dr, the proportion of infected nodes of that degree is 0 at this endemic equilibrium. For degrees less than or equal to dr, the proportion of infected nodes would be same as the proportion of infected nodes at the endemic equilibrium of this simpler dynamics. Okay. So that is the main result for this part. So before I move to part 2, if you have any questions, please ask. Okay, since I don't have much time, so I'll try to briefly go over this part. So in this part, we consider the case where nodes do not start to play their equilibrium strategy straight away, but they try to learn these equilibrium strategies following certain evolutionary dynamics. So we consider a much simpler setting here. So we consider a large population of homogeneous individuals, and each individual chooses to adopt protection or to remain unprotected. Based on their decisions, we have a population state at time t, represented by xt, which captures the proportion of susceptible individuals who remain unprotected, susceptible individuals who adopt protection, infected individuals who remain unprotected, and infected individuals who adopt protection, and so on. So XSU plus XSP is essentially ST, that is the proportion of susceptible individuals in the complete population, and so on. Now, once again, nodes choose whether to adopt protection or not. This is similar to whether to activate or not activate. Now, if an infected individual remains unprotected, it transmits infection at rate beta u. And if it adopts protection, it transmits infection at rate beta. So P would be less than or equal to beta u. You can consider a special case where beta p equal to 0. That is, the person is vaccinated, will not transmit infection at all, but although that's not strictly true. Now, for a susceptible individual, if it adopts protection, it is alpha times less likely to become infected compared to a susceptible individual who does not adopt protection. Now, adoptive protection comes at a cost, and for susceptible nodes, which they balance with the perceived loss or the expected loss of becoming infected. So this payoff vector essentially states what is the payoff of a node which is susceptible and remains unprotected given the population state x, which is defined as minus L times the possible risk of becoming infected, which is beta u times the proportion of nodes who are infected and unprotected, plus beta p times the proportion of nodes who are infected and protected, and so on. So for susceptible nodes adopting protection, this is reduced by a factor alpha, but there is a cost that you pay for being protected. So that it could be the discomfort due to wearing masks or adhering to social distancing, and so on. To simplify the notation a little bit, we mainly keep track of two quantities, Zs and Zi, where Zs is the proportion of susceptible individuals who remain unprotected, and Zi is the proportion of infected individuals who remain unprotected. Now, based we can write down the epidemic evolution, that is how the proportion of infected nodes Y changes with time. In this case, we consider a continuous time model. Similarly, these quantities Zs and Zi, which represent the behavior of the individuals, we assume that they evolve following the well-known replicator dynamics. This quantity epsilon is a timescale separation variable. When epsilon equal to 1, the epidemic and the behavior evolve in the exact same speed. When epsilon is less than 1, that means the behavior evolves faster compared to the epidemic. And when epsilon is bigger than 1, then the behavior is slower. That is, the epidemic is faster compared to the behavior. So I will not take much time, but I will briefly describe two interesting phenomena that we observe. So in this slide, we assume that the behavior evolves faster than the disease. That is, the parameter epsilon is less than 1. So this red point here is the initial point, and this E3 is essentially the endemic equilibrium, where the infection level settles down at the level Cp divided by L1 minus alpha beta p. And this endemic equilibrium is also stable and attractive. However, the dynamics does not converge to this equilibrium in a smooth manner, while on the other hand, it is actually quite oscillatory. So if you see in this graph here, the proportion of infected nodes exhibits a lot of oscillation for a very long time before it settles down. And as epsilon becomes smaller and smaller, the oscillations persist for a longer and longer time period. Similarly, ZS, which is the level, which is the proportion of susceptible individuals who adopt protection, that also exhibits a lot of oscillation. Now, why that happens? So we can explain it by looking at the graph on the left-hand side, which is a graph between ZS and the factor delta F. So delta F is essentially this quantity in the bracket of the replicator dynamics. So when delta F is less than 0, that means Y is sufficiently large. That means there is too much infection, and it is optimal for the nodes to adopt protection. And the equilibrium in that case is when ZS is equal to 0, denoted by the blue line here. So the blue line is the stable equilibrium in this case, and the red line is the unstable equilibrium. Now, if you look at the starting point, because behavior is faster, then the dynamics essentially converges quickly to the stable equilibrium point at that level. And disease being the slower dynamics does not change very much. So therefore, delta F does not change very much, but ZS converges quickly to the stable equilibrium. When all the nodes adopt protection, then Y decreases, and eventually delta F becomes positive. And in that case, the stable equilibrium from ZS makes a sudden switch from 0 to 1. However, the dynamics doesn't suddenly go from 0 to 1. In fact, it continues on the unstable line for a little while and then makes a sudden transition to 1. And then finally, this process repeats itself, giving rise to this kind of oscillatory behavior. So, and I think this, now we also observe a similar behavior, although to a smaller extent, when disease evolves faster than behavior. So in this case, the behavior is the slower dynamics. The disease is the faster dynamics. If you look at the graph between Y and beta effective, so beta effective is the effective beta as a function of the behavior of the individuals. So when behavior is small, then beta effective does not change very suddenly. And Y, being the faster dynamics, quickly converges to the stable equilibrium point of Y, which is decided by whether beta effective is larger than delta or smaller than delta. Now, delta in this case is 0.1. So when beta effective is less than 0.1, 0 is the stable equilibrium point for the epidemic dynamics. So this quickly converges to 0. As delta effective becomes larger than 0.1, the endemic equilibrium becomes the stable equilibrium for the epidemic dynamics. However, the coupled dynamics doesn't really track the blue line. In fact, it continues on the unstable line for a little while and suddenly jumps to the blue line. So that means we observed a delayed convergence to the stable branch. And therefore, for the Y dynamics, what may happen is that although it appears that infection level is really low, but suddenly it may jump to a really large or a significant value. And this could happen when there is a separation or between the speed with which the epidemic spreads and people change their behavior. Now, to summarize, in the first part, we considered activity-driven networks, and we derived mean field approximations of the epidemic dynamics, characterize the quantal response equilibrium of the game when nodes choose their activation probabilities, analyzed epidemic evolution under these activation probabilities, and showed that if the loss of an infection is very high, then a smaller percentage of nodes become infected at the endemic state. In the second part, we briefly described a model where we studied coupled evolution of disease and behavior. And we show that under timescale separation, this can give rise to oscillatory behavior, both in the disease dynamics as well as in the behavioral dynamics. And currently, we are working towards extending this setup in several directions. We have also done some related work in the context of epidemics, particularly vaccination decisions, a dynamic game when nodes take decisions in a look-ahead manner, an infinite horizon stochastic game. And also we have done some work on resource allocation for containing epidemics in a centralized manner, particularly for SIR epidemics. With this, I conclude my talk and thank you.
Thank you, Professor Hota, for an engaging talk. We can take few more questions.
Yes, Professor Rajesh.
Could you go to slide 32 where there was some randomness in the switch from one equilibrium to another?
Yeah.
So is there a characterization of how long it might take? The delta F parameter, first of all, is something that I did not quite catch. So if you could explain that.
So delta F is basically the quantity inside the bracket here. So if delta F is smaller than 0, then ZS equal to 0 is the stable equilibrium for the ZS dynamics.
Okay. And so it really is, I mean, it's not a time dependence, it's a parameter dependence. And you have the oscillatory behavior. Can you go back to the delta F once? So yeah, there it is, yeah. Does the delta F change with time depending on the state of the system? That comes from the ZL, ZI, correct?
Yes, Y and ZI both change, therefore delta F also changes. But when behavior is faster, I mean, Y does not change too frequently. So therefore, at a given delta F, these individuals would converge to the stable equilibrium of ZS. And then Y is changing slowly. So slowly delta F will change. And then suddenly ZS equal to 1 will become the stable equilibrium.
So the transition just for fixed parameters, it is just a particular time at which enough of the Y changes have happened. And
yes.
That switches the time.
Yes. However, although the stable equilibrium has switched, the dynamics does not immediately switch. So it switches after a certain delay.
That is what I wanted to understand. Is there a characterization, and this is what you mentioned as well, but puzzled me a bit. Is there a characterization of the delay, or is it from one realization to another? Does it change? Where is the randomness coming from?
Yes. So this phenomenon is actually known as bifurcation delay in nonlinear dynamics. There are certain results which define some bounds. So like some bounds on the time after which this bifurcation delay will occur. However, for the class of bifurcation that is introduced by this coupled dynamics, we could not find any result in the literature which will have a direct characterization of it. So we are currently working towards it.
And when the transition happens,
yes.
Can you characterize the transition? It always happens in this particular way and there is not much deviation. So in some sense, there is invariance in the way it transits, though not in the time.
Can you please tell a bit
from the point where ZS becomes 0.1 to the point where ZS becomes 0.9, that transition is always identical. When it gets to 0.1 may be different, but once it gets to 0.1, there is a common way by which it goes. Is there such a phenomenon?
Yeah, it appears to go up straight away because ZS is the faster dynamics. So at this point, Y does not change very much. And Jedi actually converges quickly to it. So Jedi only has 0 as the stable equilibrium point, depending on the value of CIP and CIU. So Jedi quickly converges anyway. And after that, delta F only depends on Y. Now, when Y is the slow system, and for epsilon very, very small, then Y does not change very much. So it appears to be almost vertical transition for epsilon very small. However, for epsilon equal to 1, that is this brown line here. So it is not that vertical. So it actually is a bit more like a curved shape. But for the pink line, when epsilon is very small, it appears vertical because Y does not change at all. So delta F does not change at all, and then ZS goes straight up to the stable point.
Okay, so the evolution is parameterized by Y. Okay, all right, thank you.
Yeah. Yes, any other question?
Thank you, Professor. Once again, we would like to thank you for being a part of the seminar series. And as discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details, and the links have already been pasted in the chat box. The link to the recorded video will be also posted on the web page. Thank you, everyone, and have a great evening.
Thank you all very much. It's great to present and receive your valuable feedback. So hopefully travel will become normal and we'll meet some of you in person. So thanks a lot.